Hi everybody, I am Lap-Loi Chung from the National Center for Research on Earthquake Engineering and from the Departments of Civil Engineering, National Taiwan University and National Cheng Kung University. This is my name in Chinese, Zhong Li Lai. Welcome to the course Introduction to Seismic Design of Structures. This is lecture 3-2. Force vibration of undamped single degree of freedom structure 2. Undamped structure is a structure without damping. Single degree of freedom structure is a structure which displacement can be described by only one variable. Force vibration is the vibration induced by external forces. In the last lecture, in the previous lecture, that's lecture 3-1, we have solved the problem of force vibration directly by ordinary differential equation. In this lecture, we'll introduce another alternative method to solve the force vibration problem. The method is Laplace Transform. A single degree of freedom structure can be modeled by mass m and stiffness k. This structure has no damping, therefore it's called undamped structure. M is the mass of the structure, K is the stiffness of the structure, F is the external force of the structure, X is the displacement of the structure. Because it's a single degree of freedom structure, the displacement of the structure can be described by only just one variable, xt. The motion equation of this undamped single degree of freedom structure can be described as mx double dot plus kx equal to ft. Mx double dot is the inertial force of the structure, kxt is the restoring force of the structure, ft is the external force of the structure. This is a second order, the ordinary differential equation, non-homogeneous, because the forcing function is non-zero, with constant coefficient because m and k are constant. They do not vary with time. In addition to the solution by direct ordinary differential equation, we introduce another method called Laplace Transform. If ys is the Laplace transform of yt, by the definition of Laplace transform in engineering mathematics, ys equal to Laplace transform of yt equal to integration from 0 to infinity, exponential minus st, yt dt. Before Laplace transformation, yt is a function of t. After Laplace transformation, ys becomes a function of s. Let us consider unit step function first. Unit step function is a function when t is negative, the function equal to 0. When t is positive, the function equal to 1. When t equal to 0, there's a jump from 0 to 1. The height of the jump is 1 unit. Therefore, it's called unit step function. Let us find out the Laplace transform of this unit step function. By definition, the Laplace transform of ut equal to us, equal to integration from 0 to infinity, ut exponential minus st dt. If we consider the integration range from 0 to infinity, that is t is positive. When t is positive, ut equal to 1, therefore equal to integration from 0 to infinity, exponential minus st dt. And the integration becomes exponential minus st divided by s. When t tends to infinity, if s is positive, exponential minus infinity tends to 0. Therefore, this term vanishes when t tends to infinity. When t tends to 0, when t equal to 0, exponential of 0 equal to 1. Therefore, the Laplace transform of ut equal to us equal to 1 divided by s. Then we have Laplace transform of ut equal to 1 divided by s. Laplace transform of ut equal to 1 divided by s. If the forcing function is a unit step force, the second order differential equation can be written as mx double dot plus kx equal to ut. And now we take the Laplace transformation for this motion equation. Mx double dot plus kx equal to ut. The Laplace transform of the second derivative equal to s squared xs minus s times x of 0 minus x dot of 0 plus omega 0 squared times the Laplace transform of xt equal to xs. The Laplace transform of ut equal to 1 divided by s, therefore equal to 1 divided by ms on the right hand side of the equation. From this equation, we can solve for xs equal to 1 divided by m times 1 divided by s times s squared plus omega 0 squared. Then we can perform the Laplace inverse transform so that we can find the displacement function. And here's the Laplace transform of xt equal to 1 divided by m and 1 times 1 divided by s times s squared plus omega 0 squared. And from partial fraction, this fraction can be decomposed into two fractions. One is 1 divided by s, the other is s divided by s squared plus omega 0 squared. And from this formula, the Laplace transform of ut equal to 1 divided by s. Therefore, the inverse Laplace transform of 1 divided by s equal to 1 if we just consider the positive term. And the Laplace transform of cosine omega 0t equal to s divided by s squared plus omega 0 squared. Therefore, s divided by s squared plus omega 0 squared, the inverse Laplace transform equal to cosine omega 0 squared. Finally, we can have the displacement function xt equal to 1 divided by k times 1 minus cosine omega 0t. And this is the displacement solved by Laplace transform. In the previous lecture, we solved the same problem directly from ordinary differential equation. And we have the answer to this problem in page 9. You can compare these two answers. If these two answers are the same, therefore we use two methods to solve the same problem and have the same answer, so that we are so confident that this answer is correct. Let us move to unit impulse function. For unit impulse function, when t is non-zero, no matter t is negative or t is positive, delta t equal to 0. When t equal to 0, delta t tends to infinity. And if you integrate delta t from 0 minus to 0 positive, that means that we integrate a little bit to the left, from the left of the 0 to the right of the 0, we have equal to 1. Therefore, it's called unit impulse function. If we take Laplace transform of this unit impulse function, we have delta s equal to integrate from 0 to infinity, small delta t exponential minus st dt. Because delta t is equal to 0 when t is non-zero, so that we can reduce the integration range from 0 to infinity to from 0 negative to 0 positive. Therefore, we can minimize the range of integration. And in this small range of time, exponential minus st is a constant, because exponential minus st is a continuous function. And in this small interval of time, exponential minus st equal to exponential minus s times 0. And then it can be taken out from the integration. because it's no longer function of time. Therefore, we have exponential minus S0 equal to 1 times exponential integration from 0 minus to 0 positive delta t dt. And from the definition of unit impulse function, this integration equal to 1. Therefore, the Laplace transform of unit impulse function equal to 1. Therefore, the delta t, the Laplace transform of delta t equal to 1. And then we are going to study unit impulse response. That means that the forcing function is assigned to be delta t, so that we can have the second order differential equation mx double dot plus kx equal to delta t. And the initial conditions are x0 equal to 0, x dot of 0 equal to 0. Now we take the Laplace transformation to this differential equation. Laplace transform of the second derivative equal to s squared times xs minus s times x of 0 minus x dot of 0 plus omega 0 squared times xt, the Laplace transform of xt equal to xs, equal to 1 divided by delta t, the Laplace transform is 1, therefore is equal to 1 divided by m. Because of 0 initial condition, this term vanish, this term vanish. Therefore, we can solve for xs equal to 1 divided by m times 1 divided by s squared plus omega 0 squared. Now we are going to take the inverse Laplace transformation. Xs equal to 1 divided by m times 1 divided by s squared plus omega 0 squared, because the Laplace transform of sine omega 0 t equal to omega 0 divided by s squared plus omega 0 squared, in order to make the form equal to the Laplace transform of sine omega 0 t, so that we multiply the numerator by omega 0. As well, we multiply the denominator with omega 0. Therefore, this equality still holds. And the inverse transformation of this term equal to sine omega 0 t. Therefore, we have xt, the displacement function, equal to m divided by m omega 0 times sine omega 0 t. We solve the same problem by ordinary differential equation directly. And the answer is stated in the previous lecture, 3-1, page 12. You can compare these two answers. If these two answers are the same, and we solve the problem with two methods and have two answers, so that we are so confident that the answer is correct. And then we move to unit sinusoidal function. And omega here is the excitation frequency. And 1 here is the amplitude of the sinusoidal function. Therefore, it's called unit sinusoidal function. Now we consider the motion equation. The forcing function is assigned by sine omega t, so that we have mx double dot plus kx equal to sine omega t. Here, the excitation frequency omega is not equal to the structural frequency omega 0. And there are two initial conditions. X of 0 equal to 0, x dot of 0 equal to 0. Therefore, we have 0 initial conditions. And here's the motion equation. And we take Laplace transformation for the motion equation. The Laplace transform of the second derivative equal to s squared times xs minus s times x of 0 minus x dot of 0. Omega 0 squared times xt, the Laplace transform of xt equal to xs. And the Laplace transform of sine omega t equal to omega divided by s squared plus omega squared. Because of zero initial conditions, therefore x0 vanishes. x dot of 0 vanishes. Therefore, we can solve for xs equal to 1 divided by m times 1 divided by s squared plus omega 0 squared times omega divided by s squared plus omega squared. And then we are going to take inverse Laplace transformation. Because from the Laplace transformation here, Laplace transform here, it's not that easy to find out the inverse Laplace transform. So that by partial fraction, we decompose this fraction into two fractions. One is omega 0 divided by s squared plus omega 0 squared. The other is omega divided by s squared plus omega squared. From the formula for the Laplace transform of psi omega t, we know that the inverse Laplace transform of omega 0 divided by s squared plus omega 0 squared equal to psi omega 0 t. The inverse Laplace transform of omega divided by s squared plus omega squared equal to psi omega t, so that we can find out the displacement function for the unit sinusoidal response. And here is the displacement function from the unit sinusoidal response. And we solved the same problem in the previous lecture. This is lecture 3-1 directly by ordinary differential equation. Then we can compare these two results. One result is from Laplace transform. One result is directly from ordinary differential equation. That's stated in page 19 of the previous lecture. If these two answers are the same with two different methods, so that we are so confident that this answer is correct. Then we move to another case that the excitation frequency is the same as the structural frequency, so that the motion equation becomes mx double dot plus kx equal to psi omega 0 t. And the initial conditions are x of 0 equal to 0, x dot of 0 equal to 0. So that we take the Laplace transformation for the motion equation. We divide the motion equation by m first, so that we have x double dot plus omega 0 squared xt equal to 1 divided by m psi omega 0 t. The Laplace transform of second derivative equal to s squared times xs minus s times x of 0 minus x dot of 0 plus omega 0 squared xt, the Laplace transform of xt equal to xs. And then we move to the right hand side of the equation. The Laplace transform of psi omega 0 t from this formula equal to omega 0 divided by s squared plus omega 0 squared. Because of zero initial conditions, x0 equal to 0, x dot of 0 equal to 0. Therefore, these two terms vanish. And then we can solve xs equal to 1 divided by m times omega 0 divided by s squared plus omega 0 squared and square again. Now we are going to find out the inverse Laplace transform of xs to obtain the displacement function in the time domain. Before taking inverse Laplace transformation, we have to study the formula here. The Laplace transform of tyt equal to minus dys with respect to s. From the definition of Laplace transform, ys is the Laplace transform of yt equal to 0 integration from 0 to infinity yt times exponential minus st dt. If we differentiate ys with respect to s, so that this term, only this term is function of s, the differentiation of exponential minus st equal to minus t times exponential minus st. If we rearrange this term, we have integration from 0 to infinity, tyt exponential minus st dt equal to minus dys ds. Therefore, from the definition of Laplace transform, here is the Laplace transform of tyt. Therefore, the Laplace transform of tyt equal to minus dys ds. We are going to making use of this formula to find out the Laplace transform of t cosine omega t. The Laplace transform of t cosine omega t equal to, because the cosine omega t, the Laplace transform is s divided by s squared plus omega squared. Therefore, the Laplace transform of t cosine omega t equal to minus d s over s squared plus omega squared ds. That means that we differentiate the Laplace transform with respect to s. And after differentiation, we have s squared plus omega squared divided by s squared plus omega squared and square again, so that we can conclude that the Laplace transform of t cosine omega t equal to s squared minus omega squared divided by s squared plus omega squared and square again. We are going to make use of this formula to find out the inverse Laplace transform of xs in order to obtain the displacement function. And here's the Laplace transform of xs. And this fraction is decomposed into two fractions by partial fraction. One of the fraction is omega 0 divided by s squared plus omega 0 squared. And the other fraction is s squared minus omega 0 squared divided by s squared plus omega 0 squared and square again. And from the formula for the Laplace transform of sine omega 0 t, we know that this is the Laplace transform of sine omega 0 t. From the formula of t cosine omega 0 t, the Laplace transform of this formula, we know that this fraction, the inverse Laplace transform of this fraction is t cosine omega 0 t. And finally, we get the displacement function equal to 1 divided by 2m omega 0 squared times sine omega 0 t minus 1 divided by 2m omega 0 t cosine omega 0 t. And this is the solution by Laplace transform. In the previous lecture, that's lecture 3.1, we solved the same problem. That's unit sinusoidal response directly from ordinary differential equation. And the answer is stated in page 24. And we can compare to these two answers. If we use two different methods and come up with the same answer, so that we are so confident that this answer is correct. And here's an example. There's a force vibration of an undamped single degree of freedom structure. And the single degree of freedom structure can be modeled by mass m and stiffness k. And Ft here is the external force, and Xt here is the displacement of the structure. In this example, the mass m equal to 2,000 tons. The stiffness k of the structure equal to m times 2 pi square equal to 789.57 kilonewton per meter. From the stiffness k and the mass m, if we divide k by m and then take the square root, we can come up with the natural frequency equal to 2 pi equal to 6.283 radian per second. And from the angular velocity, from the angular frequency, we can have the frequency f0 equal to omega 0 divided by 2 pi equal to 1 hertz. There's 1 cycle per second. And from the frequency, we take the reciprocal. we can have the natural period T0 equal to 1 divided by F0 equal to 1 second. Let's consider the first external force, and it's a unit step force, but it has been amplified by 2,000 tons. Therefore, UT equal to 0 when T is negative, and UT equal to 2,000 kilonewton when T is positive. And there are two initial conditions: initial displacement x of 0 equal to 0, initial velocity x dot of 0 equal to 0. We can solve for the displacement, velocity, and acceleration either by Laplace transform or directly by ordinary differential equation. We can have the displacement, something like that, and we observe the displacement equation here. It vibrates with frequency 2 pi radian per second, but it does not vibrate above 0. It vibrates above 0.025 meter. And if we observe the velocity here, it also vibrates at the structural frequency omega 0. That's 2 pi radian per second, and the amplitude of the velocity equal to 0.1592 meter per second. And we observe the acceleration. It also vibrates at the frequency 2 pi radian per second, and the amplitude of the vibration equal to 1 meter per second square. And here are 3 plots for the displacement, velocity, and acceleration. First of all, we observe the initial condition here. The initial displacement equal to 0, and the initial velocity is also equal to 0. And then we observe the period of the vibration. For one cycle, to complete one cycle of vibration, it takes 1 second. Therefore, the period of vibration equal to 1 second. And then we observe the amplitude of the vibration. For the displacement, it does not vibrate above 0. Instead, it vibrates above 0.025 meter, and it vibrates in the range from 0 to 0.025 meter. And then we observe the amplitude of vibration for the velocity is about 0.1592. From the previous slide here, the amplitude of vibration for the velocity is 0.1592. Therefore, the amplitude is very close to 0.16. And then we observe the acceleration. The amplitude of acceleration is 1 meter per second. And then it's consistent with the formula here. Therefore, we are quite sure that the plot is correct. And then we move to impulse response. And this impulse is no longer unit impulse because it has been amplified 200 times. Therefore, Ft, external force, equal to 200 delta T. The unit of the force is kilonewton. And we have two initial conditions. Initial displacement, x of 0 equal to 0. Initial velocity, x dot of 0 equal to 0. Then we can solve for the displacement, velocity, and acceleration either directly from the ordinary differential equation or Laplace transform. And we observe xt. xt vibrates with a frequency omega 0. Omega 0 is the structural frequency equal to 2 pi radian per second. And the amplitude of the vibration is about 0.016 meter. And we observe the velocity. Omega 0 is the vibration frequency equal to 2 pi radian per second. And the amplitude of the velocity equal to 0.1 meter per second. And then for the acceleration, the frequency is 2 pi radian per second. And the amplitude is about 0.6283 meter per second square. And here are the 3 poles of displacement, velocity, and acceleration. First of all, we check the initial displacement, 0. And the initial velocity is about 0.1 meter per second. and because of the force is being unit impulse response, because the force is an impulse force, therefore the initial velocity a little bit larger than 0 is non-zero. And then check the amplitude, the period of the vibration. It takes 1 second to complete 1 cycle of vibration. It takes 1 second, 1 second here. Therefore, the period is consistent what we expected here. And then we check the amplitude for the velocity. 0.1 meter per second is 0.1 meter per second. They are consistent. And check the amplitude for the acceleration is about 0.6 and is consistent with what we expected. Therefore, we are quite sure that these plots are reasonable. And then we move to sinusoidal response. And the sinusoidal force is no longer unisinusoidal force. It has been amplified 2,000 tons. Therefore, the external force Ft equal to 2,000 sine omega t. And the unit is kilonewton. And we have two initial conditions. X of 0 equal to 0, x dot of 0 equal to 0. By the method of solving directly the ordinary differential equation or Laplace transform, we can have displacement, velocity, and acceleration. And omega here is the excitation frequency equal to pi radian per second. When we observe the displacement function, is equal to, here we have sine 2 pi t, and here we have sine pi t. Here's the structural frequency, 2 pi radian per second. Here is the external excitation frequency, pi radian per second. Similarly, for the velocity and acceleration, we have two frequencies. One is the structural frequency, 2 pi radian per second. The other is the excitation frequency, pi radian per second. Since the period for 2 pi radian per second equal to 1 second, and the period for pi radian per second equal to 2 seconds, therefore the least common multiple is 2 seconds. And then we can observe here the period for displacement equal to 2 seconds. From 0 second to 2 seconds, you repeat again. And the period for velocity is also 2 seconds. And the period for acceleration is also 2 seconds. And then we check the initial conditions, initial displacement equal to 0, initial velocity equal to 0. And this is the excitation. That's the external force for this example. Now we change the excitation frequency to 2 pi radian per second. Therefore, the excitation frequency is the same as the structural frequency. And we have two initial conditions, x of 0 equal to 0, x dot of 0 equal to 0. By solving the differential equation, no matter directly by solving the ordinary differential equation or the Laplace transform, we can have the structural displacement, structural velocity, and structural acceleration. When we observe the displacement function here, we have sine 2 pi t, cosine 2 pi t. Therefore, the displacement vibrates at the structural frequency, 2 pi radians per second. And then we observe the amplitude of the vibration. This amplitude is constant, but the amplitude here is a function of time. Therefore, the amplitude increases linearly with time. Therefore, the amplitude for the displacement becomes larger and larger as time goes by. We have the similar observation for the velocity equal to 0.5 t sine 2 pi t. Therefore, the frequency is 2 pi radian per second. The amplitude is 0.5 t. Therefore, it's a function of time. It increases with time. It's linearly related with time. Therefore, the amplitude becomes larger and larger as time goes by. Similar observation from the acceleration. The first term the amplitude here is a constant. But the second term, the amplitude here is a function of time. It increases linearly with time. And the frequency of vibration are 2 pi radian per second, because the excitation frequency is the same as the structural frequency. Therefore, no matter for the displacement, velocity, or acceleration, there's only one frequency. And here's the external force, and here's the plots for the displacement, velocity, and acceleration. Let us consider the period first. From here to here, 1 second, 1 second, 1 second, 1 second, 1 second, 1 second. Therefore, the period of vibration equal to 1 second. And then we observe the amplitude of the vibration. It becomes larger and larger, and is linearly or proportional to t. That means that as t becomes larger and is linearly with the time, therefore it becomes larger and larger. Let's consider another case. Here, the excitation frequency is equal to 3 pi radian per second, and the two initial conditions are 0. By solving the differential equation, no matter directed by ordinary differential equation or Laplace transform, we can have the structural displacement, structural velocity, and structural acceleration. By observing the displacement function here is psi 2 pi t, the structure, the displacement vibrates at frequency 2 pi radian per second. That's the structural frequency. And here, the displacement vibrates at 3 pi radian per second. Here is the excitation frequency. This is the structural frequency 2 pi. This is the excitation frequency 3 pi radian per second. Same for the acceleration. 2 pi is the structural frequency. 3 pi radian per second is the excitation frequency. The period for 2 pi radian per second equal to 1 second, and the period for 3 pi radian per second is 2/3. Therefore, the least common multiple for 1 second and 2/3 second is 2 seconds. Therefore, the period for the displacement function equal to 1 second. 2 seconds here, and then it repeat again at 4 seconds. 2 seconds here, and then it repeat again at 4 seconds. Here is a t equal to 2 seconds, and then it repeat at t equal to 4 seconds. Therefore, the period for displacement, velocity, and acceleration are 2 seconds. And here's the excitation frequency. Excitation, that's the external force, with frequency 3 pi radian per second. And here are some references. The first reference is Seismic Design Codes of Buildings. It's published in 2011 by the Ministry of Interior. It can be downloaded from this website. And the second reference is Ordinary Differential Equation. It can be found out from any textbook on engineering mathematics. Another reference is on Laplace Transform. You can find it out from textbook on engineering mathematics. And here are some videos. There's the video for lecture 2-1, English version, Chinese version. And here's the video for lecture 2-2, English version, Chinese version. There's the videos for lecture 3-1. There's the English version, there's the Chinese version. And that's the video for lecture 3-2. The English one is the current one. We don't have the website yet because it has not been uploaded to the YouTube. And this Chinese version, it has already been uploaded so that you can watch the video from this website. And here's the video for lecture 4, English version and Chinese version. In this lecture, we study the force vibration of undamped single degree of freedom structure, and we solve this problem by Laplace transform, in addition to the method in the previous lecture. From this lecture, we use Laplace Transform so that we solve for the unit step response under unit step force. We solve for unit impulse response under unit impulse force. We also solve for unit sinusoidal response under unit sinusoidal force. That's all for this lecture. Thank you. See you next time. Bye-bye.